Hello everyone, my name is Mo Syed and I am an AGI Systems engineer supporting users across the Northeast and the Southeast of the US. Thanks for that awesome introduction, Dwayne. Today I'm here to talk about digital mission engineering, or DME for short, and how its ideas and goals offer a very distinct advantage in the ever-evolving aerospace and defense industries. To effectively highlight these concepts and apply it to a topic that is quite pervasive, we will assess the mission performance of a hypersonic system with a focus around AGI Systems Toolkit, or SDK for short. And then here we'd just like to put a face to our names, just so you can get an idea of who's presenting. So here we just have the agenda for today. First, we will go into some of the challenges that are faced by the industry and government. This will lead us into the discussion about digital mission engineering. From there, we will further elaborate on DME by going through an example. This example will be exploring portions of the engineering lifecycle with a focus on the hypersonic technologies, and then from there, we will go into any questions or any next steps. So, some of you may be asking, why DME, or why now? Well, for those unaware, a quick look at the news or a Google search will show you multiple articles containing headlines like the ones you see here in the slide. America's preeminence in missile technology is being challenged for the first time since the end of the Cold War. Alongside the United States, the Russian Federation, and the People's Republic of China are currently developing hypersonic weapon systems designed to defeat existing missile defenses through incredible speed, up to 27 times the speed of sound, and high maneuverability. No effective countermeasures currently exist against these weapons. We have to ensure that as new challenges arise, that we are up to the task and that we do not get left behind. As the world continues to change and evolve, we have to understand that we need to go even faster than ever as well. So we are seeing these new challenges and threats emerge, but we also have to talk about some of the challenges that we currently and have previously faced. Various studies across the industry have been conducted, and in particular, the Standish Group found that 82% of effort on software projects goes right into maintenance and testing. Now, this could be due to a number of reasons, such as having code that is stovepiped or one-off tools and software, or a piece of code that is repurposed for a use case entirely different than what it started out for. This has led some organizations to have mission-critical pieces of code that only a single individual knows how to run because they wrote it some 10-odd years ago. Another issue is that a lot of programs or projects have initial requirements that don't fully capture the scope of the project, and changes had to have been made. I'm sure many of you are familiar with scope creep. Because of this, we aren't even getting a one-to-one increase in production when we get that increase in staff. Another study concluded that a 50% increase in staff is only leading to a 20% increase in production. Lastly, the marketplace is completely changing. Defense and intel customers aren't willing to accept good ideas if it costs a program delay to implement these ideas. Due to this, we all find ourselves at a very interesting time in our industry. However, we have and will always have new challenges to face, and like always, we will come up with a solution. But that raises the question of, what should a solution to these challenges look like? Well, we've listened to what has been said across industry, and here's what we really came up with. A solution should include a limited set of open, highly capable tools that are tightly integrated across all phases of a program and even across different programs. This is important both for the continuity of highly interdependent programs, but also to minimize the ramp-up of personnel as they transition from program to program. To that end, really, a solution must be open to custom data and leverage common data standards to integrate with tools like MBSE or even your proprietary models. This way, your engineers can focus on the secret sauce that makes your organizations unique versus trying to maintain some old code or currently recreating a duplicate model that was already used for a different program or project, or etc. Additionally, a solution should include a sophisticated analysis environment that can enable large-scale trait studies where design parameters can really be evaluated against mission performance metrics from all levels of modeling. This can be at the system level, component level, and even campaign level of modeling. So along with that, this analysis must rely on rapidly modeled, accurate dynamics of any platform performing the mission. It does not matter if it's modeling a friendly or adversarial entity, a spacecraft, an aircraft, or etc., using either simulated or even ingested real data. And this is where collaboration becomes very, very critical. As your engineers, scientists, specialists make those changes in their own domain, those changes must seamlessly ripple through to the specialists in the other domains, instead of having to schedule a meeting or emailing an individual on the other team informing them of the update and make sure that they receive it in a timely manner. For example, if your communications team makes a change to the antenna size, how does that change affect the link to the aircraft? Will this introduce more dropouts? These are the kinds of changes in parameters that you would want to seamlessly flow through your entire engineering lifecycle to see how, at the end of the day, that mission is impacted by your antenna change. Finally, the whole solution must be validated and trusted across a wide variety of complex problems. This will help keep the focus on addressing those new challenges and not building and accrediting new tools every time. Along with this, the solution must be well documented and supported so your engineers can learn and get up to speed without bringing down your own highly valued subject matter experts. And of course, a solution that does all of these wonderful things should make you more competitive by providing faster results at lower costs and higher fidelity than your competitors. This way you really can highlight the value you bring to the mission, which will help win business and win the trust of your customers along the way. So, this basically brings us to the concept of digital mission engineering and even digital mission operations. Digital mission engineering is the use of computer-based modeling, simulation, and analysis tools to incorporate the operational environment and evaluate mission outcomes at every single phase of the engineering lifecycle. So not just in design, not just in testing, not just in operations. When programs are created, they are meant to meet a need, a gap, a requirement that will help achieve the desired mission objective. Programs aren't necessarily created just to create the coolest new aircraft, the coolest new tracking system, just because we can, as cool as that is. There's an underlying purpose that guides every task, every assignment, and every decision, and it's the mission. It always comes down to evaluating the mission outcomes. Okay? So if we were to try to keep that in mind and take a look at this bird's eye view of digital mission engineering, is even though the mission is of utmost importance, DME is comprised of integrating or seamlessly integrating the mission models with the system models, subsystem models, and even to that component level of modeling into one physics-based construct. To really do this successfully at each level, we create what's known as a digital twin, or a digital representation of our component, system, or even systems of systems. The purpose of course here is to really evaluate mission effectiveness while at the same time component effectiveness, all in a single user domain. Remember, it's about keeping this as seamless as possible. So now to reframe the question of why now, or going back to why DME is important now, based on everything we talked about, is really for two big reasons here. There really isn't a tolerance anymore for lengthy program timelines, and the complexity level of these programs is increasing dramatically, which all points back to an acceleration of national security threats. So these programs are not only having shorter timelines, but the complexity to achieve the results or so forth are so much more advanced. We can't really have an incremental change here and there to update our current methodologies. We need to implement a revolutionary improvement approach. And it's not just us who think this way. On the screen here, you can see that there is a DES, or Digital Engineering Strategy mandate, that has been sent out by the DoD. These are objectives from Dr. Will Roper, who is the Assistant Secretary of the Air Force for Acquisition, Technology, and Logistics. And even though this isn't an Air Force-specific event, the concepts and practices from Dr. Roper should really resonate across all of aerospace and defense. Our adversaries are seeing the benefit of going faster, and we need to change up our game to make sure that we are too. You can see here in the highlighted pieces that the department is transforming its engineering practices to digital engineering, incorporating technological innovations into an integrated digital model-based approach. So we are seeing many folks across industry, even in government, kind of now adapting and going with this new digital engineering strategy or digital mission engineering approach. So really, here's a depiction of that program lifecycle. And ideally, what you want to see is a physics-based models and simulations tying each phase together and really being focused on those mission outcomes, right? But instead, here's what it currently looks like for most programs. Based on what we've learned by supporting the aerospace and defense industry for 30 years, the current process is one where models are disparate for the overall systems, subsystems, and components. They are disconnected from each other and physics-based simulations, and sometimes both are disconnected from the requirements piece. There's not really a continuity thread across the different stages, not in terms of really the models and not even in terms of the physics tools. So you're ending up creating new models at every single stage, and everything is being held together by human glueware, which could be, dragging and dropping one file into an email to pass to a colleague, going through a filing cabinet for a document containing important pieces of information, so forth. And then the result is, well, as we saw and as we described based on some studies in previous slides, is that we see a heavy amount of delays and duplication of those efforts. These critical issues that we're talking about that we were talking about a moment ago, like I was saying, there's not really a shot of identifying them early on, much less really handling them in an effective manner. So the rhetorical question here is, how will this all affect the mission outcomes? And as we said, it's a completely broken process. What we have here is we have this vision to achieve better decisions sooner. Process changes and the right tools are important. What we see here in this vision is, unlike the previous life cycle, there aren't going to be any broken lines as we frequently see today. The goal is to maintain a persistent model from the concept through sustainment so that there is traceability back to the mission outcomes. Always about the mission, remember that. And these models can be descriptive models, calculation analytical models, behavioral models, or really anything that we discussed in our definition of DME. The goal here is to have a persistent model that brings as much high-fidelity modeling and simulation as far forward or to the left of the influence effectiveness curve. So we need to make sure that all of these seamless models are always communicating and connected to that multi-domain physics environment to really achieve those physics outcomes. Having that multi-domain physics environment or ecosystem is very important to ensure that that will help us really knit through the fabric of the digital thread through the life cycle. So far, at this point, what we've discussed is an overview of DME and why it's very important right now. And now, for a moment, I really want to move on and show you what our vision of DME looks like and how AGI and SDK really fit in and play a fundamental role in all of that as well. So as we jump into the Hypersonic example, you will notice that almost every stage is constructed or has a piece that is analyzed using SDK. So before we really jump in it makes sense to provide some context for what SDK really is. Many folks know us for satellite visualization, but AGI SDK is much, much more than that. We are a multi-domain type of tool that can analyze both or all land, sea, air, and space platforms, as well as subsystems going from EOIR sensors, communications and radar platforms, propulsion systems, etc. And more impactfully, we fuse all of these disparate or various elements into a single common environment that's physics-based, where we can analyze the interactions that are taking place between the various component levels models, the subsystem level models, and system of systems levels models. From using SDK, we also can extract out over 40,000 performance metrics to ensure that you are getting exactly the information and data you need to ensure mission success. Along with that, we know that a lot of folks, like we were saying before, have their own secret sauce, and SDK has flexible form factors and APIs to really allow you to bring in your own data-driven custom models that we can then use to integrate with the current models that are built within SDK. For all of these reasons, really, AGI software has become an instrumental component to modern engineering solutions, as it really helps the engineers, the scientists, and those analysts and operators make better and more informed decisions regarding all of the subsystems and platforms as they're interacting with one another through both space and time. We really believe that SDK has an important and revolutionary role to play in the field of DME for the years to come. All right, so now we're just going to jump into the hypersonic mission modeling example with everything that we've established about SDK and digital mission engineering. For our example, we will use NASA's 2004 X-43 hypersonic glider flight as an example. And with this, we will model the flyout as well as the various systems and subsystems will interact with the X-43 in the operational environment. So, just to highlight what was in the agenda, we're going to break this up into 3 portions. We're going to have the aircraft design, the thermal analysis, and the communications. Now, of course, this may not encompass every part of the hypersonic engineering lifecycle, but for our time that we have here today, we felt that this will be good enough to really get a better understanding of how digital mission engineering can raise the efficiency and effectiveness of your engineering analyses. So, we're going to start off first with aircraft design and really focus on the trajectory, CFD, flight profile portion of it. So going into the flight capabilities is with SDK Aviator, we have the ability to define realistic models and performance characteristics for highly accurate time-based aircraft route analysis. Within the module, the user can really define the aircraft model, the performance model, and flight sites, as well as procedures to fully outline the aircraft's mission. And in that aircraft model, we can define the physical characteristics of the aircraft, as well as the modes of flight that define how the aircraft flies in any given situation. Not every single maneuver an aircraft will take will have the same type of control surfaces deployed, etc., and all of that can be taken into account. Performance models are really used to define the behavior of this aircraft, so by specifying the performance, like I was just saying with the control surfaces, in every phase of the mission, we can change the manner in which the aircraft is actually performing the mission based on the priorities of the mission. So this can include models such as modeling the takeoff, climbing, cruising, acceleration, descent, and landing, with parameters to be influenced such as the bank angle, turn radius, roll rate, as well as other various aerodynamics and propulsions of the aircraft as well. We also can model the fuel as well as the fuel distribution and model some of the operational environment, because a flight won't always be in smooth, calm air. You have the ability to model certain wind effects that would allow you to see how your fuel consumption and other parameters are being impacted. Along with that, at a very high level, we also have varying hypersonic capabilities right within the same tool of Aviator. We have the ability to model a full 3D, or Aviator I should say, has a full 3D gravity model with oblate rotating Earth effects, including some Coriolis terms, and we also give the ability to model some hypersonic power plants. Along with that, Aviator has the ability to ingest in CFD data to ensure that your aircraft models are even more accurate than what the tool can predict, especially with these new hypersonic vehicles coming out where they are being tested in CFD environments or even wind tunnels. From these, you have the ability to generate a flight envelope that will give a realistic representation of what your aircraft will be performing under in terms of the various conditions. So with all of this in mind with SDK Aviator, from both the hypersonic side and from both just the fixed-wing aircraft side, we were able to model the X-43 hypersonic vehicle's flight within STK. And more in particular, we were able to model the entire system of systems of aircraft that were used for the X-43 flight here. As you can see, we're about to take off from a runway with an SDK, and here we just have an image of the B-52 that actually flew on the flight for the X-43. So on the B-52, we have a Pegasus Stage 1 launch vehicle, or what's renamed as a HyperX launch vehicle, on the wing of this B-52 with an adapter, and the HyperX research vehicle, or X-43, on the nose. So within SDK, we were able to model both all three of the fixed-wing B-52, the Pegasus launch vehicle, as well as the X-43 research vehicle, or the actual hypersonic portion. And here you can see we have it taking off from a runway, and we have our B-52 following along a certain trajectory that we modeled. Luckily with Aviator, we don't necessarily have to just explicitly write out every single independent waypoint, and you can see that we can model the B-52 in terms of simple procedures, as taking off, flying to a waypoint, flying straight for a certain amount of time or distance, and then turning around to land. Within this flight, we have the Pegasus launcher and the X-43 deploying and flying off. So here we can already see how the operational environment is allowing us to really combine these three systems together and see how they interact with one another in terms of when one has to deploy from the other and so forth. As well as that, you can see that with Aviator, we were able to take metrics of the B-52 that we got from various papers and model it right within the software. So along with that, we can see here that after a certain amount of time that the B-52 flies, we were also able to model the launch vehicle that takes the X-43 up to altitude where it can go through its hypersonic gliding. And that's in this yellow line that we see on the screen here. So we can tell that for some moment in time, it is attached to the B-52 under its right wing, and then after a certain amount of time, it will then get deployed and launched off to get to a certain altitude of about 100,000 feet and a Mach of about Mach 10 for the hypersonic glider to deploy and go through its analysis. And here you can see, just like with the fixed-wing aircraft, the launch vehicle is modeled in a similar fashion, right within the Aviator tool, where that first section here is simply being attached to the B-52, and then the various other procedures are modeling the free fall, pull-up, and acceleration maneuvers that the Pegasus went through, based on the NASA papers that were public that we got this information from. So as you can see here at the very end, the Pegasus then just stages out and kind of lands in the ocean and it's expended. But before it does that, we have here in magenta the X-43 that was able to be deployed. So as you can see here, working within the SDK operational environment, we're able to show all three take off, and we're also able to show this X-43 deploying and get certain metrics from it. If we were to take a look at the X-43 here, you could see that really due to just the nature and the time that this experiment took place, or test took place, the hypersonic portion here is only for about 10 to 11 seconds. And the reason for that is this is technically a hypersonic glider, meaning it can't really achieve that hypersonic speed, but it can maintain it with the fuel it has on board. So before this hypersonic phase, it ejects from the Pegasus, which brought it to speed, and now here we're observing how the hypersonic vehicle behaves with the fuel it has on board and the metrics that we were able to ingest into the software. If you can look at the top left, you'll see that the initial aircraft setup is X-43 notional, meaning that we took data that we got from public NASA papers about the X-43 and ingested that into the Aviator, which was able to make a flight profile based on those metrics. This is what led us to get the flight trajectory that we do, and also points out why the aircraft lands where it does in terms of the physics that are being calculated. And here we can see we have the X-43 just after it's deployed going along its route, and you can see here it has about a 10-degree angle of attack, and we're just going to let it propagate. One thing to note is we're going to see this go through a physical motion as it's trying to maintain its angle of attack, known as a phugoid motion here, as you can see it kind of going up and down. And we did not tell the aircraft to necessarily do this. We told it to maintain an angle of attack, and it essentially is now using the physics inside built-in SDK to accurately model a phugoid motion. And here you can see that now this X-43 is now landing somewhere in the ocean. And the whole mission use case here is the engineers and analysts want to model how well that this hypersonic vehicle can be detected and a general idea of where it lands for recovery. Of course, if you are familiar with the real story, I don't believe recovery occurred in all the flights, and we may have lost some just due to them hitting the ocean. But anyways, with this X-43 notional aircraft here, you can see that we have some of the varying metrics to get from the software. We did mention that there's over 40,000 metrics, but here is just a few of them that are dealing with flight profile by time of the hypersonic vehicle. And here you can see that we're able to get metrics such as downrange, vertical speed, altitude, fuel consumed, and so forth. And of course, right at the start of the mission, the X-43 is pretty much on the hypersonic vehicle, so the fuel isn't consumed, but as we go forward, we can see it is. So here we have just a general modeling of the hypersonic aircraft trajectory portion only. And one thing to note is with SDK, we can up the fidelity as well. I did mention with Aviator that you can use CFD data to once again increase the fidelity. Unfortunately, we didn't really have the most accurate metrics that we got from the NASA papers about the lift and drag coefficients, so that is why this HyperX launch vehicle is known as the notional arrow. But what we did do is with another tool that is very, very helpful for digital mission engineering is we used ANSYS's Fluent tool for CFD modeling. And what we did is we placed in the hypersonic vehicle to get a more accurate representation at various speeds, altitudes, and angles of attack to get a more accurate representation of lift coefficient and drag coefficients. From this, we were able to import some of this data right into SDK to give a better idea of what exactly this aircraft should behave versus the notional assumptions that we got from using the information of its geometry and power plants from the NASA papers. So here we have a little bit more of a higher fidelity analyses that's going into the X-43's trajectory and flight profile, as we got it from a high fidelity component level analyses done through ANSYS with CFD. And just to kind of go forward here and show you the difference between the two is currently here we're back in our environment where we saw we had our hypersonic vehicle. We just hid the visuals of the B-52 and the Pegasus launch vehicle. But what we're going to do is compare the trajectories between the CFD version of the X-43 versus the notional that we got from the generic or the generalized papers. And here we can see that we told the CFD aircraft here to follow the exact same procedures in terms of deploying at the same time and so forth. But just due to the higher fidelity of metrics, we're able to see a disparity or a generally large difference between where the two vehicles say that they are landing. Now, in our use case, this could become very important in where some boats have to be placed in order to recover this vehicle. It's about a 92-kilometer difference. So we have to make sure that we are placing entities in that area or entities to track this in that area so that we ensure success in recovery and also success in testing various subsystems or systems that we need to test. So now we're going to move on and start talking about the thermal analyses. This includes things such as time dynamic temperatures, thermal environment, and the different sensors that we have to model in order to properly make sure that we can detect our hypersonic vehicle just based on its thermal signatures. For this, we will be using EOIR, still out of SDK. What EOIR allows us to do is do model detection, tracking, and imaging performance of EOIR or electro-optical and infrared sensors for various different applications, such as earth science, missile defense, and space situational awareness applications. So this is pretty much supported through the whole concept development, design, field, and test operations. And with EOIR, you have the ability to generate some technical metrics, such as signal-to-noise ratio, but not just data in the form of reports. You can also generate synthetic scenes or synthetic sensor images that a realistic EOIR platform would be generating. But it's all simulated, so you still can go through your parametric analyses, but still generate lots and lots of synthetic scenes and data to really make sure that you are getting the proper results. So, just kind of going into a little bit of the material modeling, so for example, how we can do the thermal modeling of our X-43 hypersonic glider. With EOIR, you have the ability to model multiple materials for a single target, kind of like we see on the target here on the right with this spacecraft. You can see how as it's orbiting and rotating, the reflectivity is changing. So each component of this target can be modeled with a various or different temperature and material characteristics to accurately reflect the various reflectivity parameters and absorption parameters each of those materials may have. Along with that, you can put in custom temperature profiles. So with EOIR, you're not necessarily just going to be looking at a static temperature, especially with hypersonic vehicles. A certain region, like the leading edge of a hypersonic vehicle, may have its temperature change drastically over time. So we give you the ability, or rather EOIR gives you the ability to really model those proper types of temperature disparities that occur over time in the software to once again really let you take a look at that whole mission level of performance characteristics. Yes, we know that our sensor can see the vehicle at its hottest, but depending on where our certain sensors are placed, are we able to even detect the vehicle when it is flying at its highest temperature? If not, can we still detect the vehicle, right? These are the kinds of questions that we're looking to hope to answer. But along with that, there is more to the operational environment. You may not have clear sunny weather every single day. In our hypersonic case, it may not be a completely clear day either. There may be some clouds in the way or so forth. But luckily, with EOIR, we have the ability to ingest in cloud modeling with a thin layer approach, as well as supporting inputs for different time dynamic layers and cloud characteristics that go through percent cloud cover, the temperature, emissivity, and radiance. Remember, we always are focused on the mission, and random bursts of bad weather are part of the operational environment. So just going back to our example with STK and really taking a look at that thermal environment, is we're seeing here a representation of the hypersonic flight, but with more entities added in. You can almost picture that the folks in charge of the aircraft now passed it off to the thermal group, who had some information about where certain satellite platforms should go and other aircraft platforms should go that would be containing some of these EOIR sensors. So for example, we still can see our initial route here with that blue B-52, the yellow Pegasus, and then the magenta HyperX research vehicle. But around it, we can see that we have a whole bunch of various entities, such as some F-18s, an RQ-4B Global Hawk, as well as a bunch of UAVs. They're all communicating via communications to a ground terminal, but they're also doing observations to the hypersonic vehicle. The hypersonic vehicle's thermal tracking lines, or just guidelines if you will, are represented by yellow, while the communication lines are represented by cyan. So since we're modeling the thermal environment, we're going to take a closer look at what the yellow lines mean and kind of how some of the spacecraft in our operational environment are interpreting our hypersonic vehicle. So we're going to take a look at LEO number 12 here, okay? And we're going to basically look at a camera, an EOIR camera that's along this yellow line, okay? And this EOIR camera has a few metrics that have been programmed in it to help us generate a synthetic scene of a certain parameter. So what we're going to do is now just go into the properties of the EOIR sensor right here, and we can see we have initial of the spatial parameters set. For example, the field of view is only 0.002 degrees in the horizontal and vertical half angle directions, had about a pixel resolution of 13, and we have all these other certain parameters that we can adjust. We only put in one frequency band here, but as you can see, we can add things such as motion blur, any types of jitter, to really, once again, make a system in STK that's a digital twin, so it must be accurately represented. With all of this running, we were kind of looking at the sensor side, but we also have to take a look at the X-43's materials side. We have the ability to set various shapes that can be as coarse or as high fidelity as we like. You can see here we have a custom mesh option to ingest 3D models, but right now we're just going to keep it at that coarse level of keeping it at a radius of 2 meters with an average temperature of 2000 Kelvin and just a gray body material. You can almost think of this as the first pass to see even if our EOIR sensors are configured properly in the first place to detect just a generic sphere. From there, that's where we can start really upping the fidelity. So if we were to take a look, taking into account the sensor parameters, the vehicle thermal parameters, as well as the atmospheric and environmental parameters, which do include things like the aerosol level, the cloud levels that we were discussing, and things like taking into account a mod-tran atmosphere, we were able to generate some notional results. And the reason I say notional is because remember that EOIR shape was simply a sphere. But here we can see that we're getting some type of notional result that is basically letting us, from that same satellite, that is essentially letting us know that indeed, based on our parameters in this run or this use case, we are able to see some type of signature from the spacecraft. So now maybe the next step for you from that thermal environment is to say, well, within STK, within our operational, multi-domain physics environment, how can I up the fidelity? How can I start bringing in more time dynamic thermal parameters so that I can more accurately analyze how well my systems can detect it? And the answer is well, we're going to use another tool that's out of our DME infrastructure, which in our case is once again using ANSYS and the CFD modeling to get a better picture of the thermal environment. So once again, while running a hypersonic vehicle through CFD, we were not only able to get various lift and drag parameters, but we were also able to connect to their thermal capabilities and get out a surface temperature distribution as this vehicle is flying out. So now in our use case, we still did make some assumptions, and one of them for us is that this hypersonic vehicle, or rather we only modeled the thermal temperatures of the hypersonic vehicle and not any of the plumes. Not saying that we cannot do that, we simply didn't for this use case. But that, of course, is that very next step of fidelity. So along with that, we did show a synthetic scene from the satellite side, but once we upped the fidelity, we just wanted to see how good of a picture we could get. So we also ran some sensor simulations from the drone that was very close by. And of course, the plume is not modeled here, but you can see that we're able to generate a synthetic scene of the X-43. So that synthetic scene is based on some of the thermal parameters that we were able to ingest in from ANSYS. But once again, it's still in that same operational environment as was that idealized thermal sphere. From there, of course, we can get these various detailed reports out of the software. So it makes it for a very ideal use case here. And just to get a better picture of exactly what we're taking a look at, here's just the more accurate results. Of course, now it's in a different color format. Previously, in the previous slide, the color map was just in a grayscale, and here it's in a BGRY. But the reason I like showing this synthetic scene is because this is essentially a synthetic scene generated right out of EOIR that allows you to click on any of these pixels to get certain metrics out, such as the spectral radiance, the in-band radiance, as well as where or what material it is and the temperature at the time. So you can essentially get all of these synthetic scenes generated and make a video that you can then compare to a real-world example to see how close it is to reality. And from this, we're now able to get a better idea of if our thermal sensors have the ability to detect, identify, and track this platform based on the certain assumptions we made and based on the parameters of our sensors. So from here, if we were to look in that whole engineering life cycle, maybe now that, since we're trying to find out where the X-43 will land, we now have a better idea of where it currently is in its flight because we have our EOIR sensors able to track it. Now, with these satellites and these UAVs that are tracking it, we need to make sure that we can pass that data or that information to the proper folks so that we can coordinate a recovery or a reconnaissance of such a vehicle. And to do that, we're going to be taking a look at the communications portion. With communications, you have the ability to model things such as antennas, link budgets, outages, and the whole really comms environment. Now, this can go all the way from using just various antenna types that are found right with an STK, such as like a parabolic, a phased array, a Gaussian antenna, all the way up to any certain custom, or once again, back to that secret sauce, type of antennas that your organization may have and want to model within the tool. From there, and just like with EOIR, you can still get out very, very extensive performance criteria, such as loss, Doppler, carrier to noise, EBNO, bit error rate, and so forth, while still taking into account the rest of the RF environment. Like we were saying for EOIR, if it is a cloudy day, it may also mean it's a rainy day. There may be some rain getting in the way, there may be some fog in the way of your actual comm analysis that may cause enough interference that could cause this mission to have some certain areas that are overlooked that need to be gone back to the drawing board to fix. Along with that, we know that the operational environment doesn't always just mean the atmosphere, right? It could be some other passive players. We saw here that we were modeling EOIR sensors on satellites that were at a LEO regime that also had some communication parameters on them. Well, the LEO regime is pretty crowded as it is, and it will get even more crowded with all the large constellations coming out, meaning that there will be interference issues that we have to make sure that we're accounting for. So luckily, through the use of comms, we can also account for certain shortcomings that are due to some passive interference or in even other use cases, some active malicious jamming that is occurring. Also, let's take a quick moment to talk about modeling the hypersonic plasma layer. We know this is a very important facet of analysis that needs to be conducted with hypersonic vehicles. In our use case, we really have been focusing on modeling the communications network for the various tracking entities. Now, with that being said, we currently do have some methods to model the losses at a mission level in the form of losses that are introduced to your link through native geometric constraints, or even using user-extensible comm loss plugins that you can program in to really introduce in that time dynamic loss due to the plasma layer. Now, along with that, we are currently working with our partners on a standard model integration, which we will hope to see in future releases to make this type of analysis more seamless with an SDK. But like I said, for our use case, we mainly focused on the communication network, but this could be another piece of analysis that gets added in to see how much the degradations from the hypersonic plasma layer affect any communications to the X-43. So for example, going back to the same use case, of course, is this time we're going to be focusing more on the blue lines. If the yellow lines were representing all the different satellites and payloads that have, or platforms that have EOIR payloads on them, now these blue lines represent all of the spacecraft and other platforms that have a communication payload on them, that are able to then coordinate some type of communication back to the main base here, or the home terminal. So initially, we just used SDK to generate a very idealized parabolic antenna, and as you can see here on the ground is the contours of its gain pattern, right? Initially, it is a very idealized, very smooth pattern that will be used for analyses with a frequency of 2.2 gigahertz, and there is even an assumption being made that this is essentially, in many facets, like a parabolic antenna or an idealized version of an antenna. So for example, we're using just an omnidirectional 2.2 gigahertz antenna. It's a very generic pattern that we made, and we're able to get very idealized results with this. So this is not the end of the world. It's just like with EOIR, showing how we start from coarse and we will eventually go all the way up to a higher fidelity. But even with the coarse analyses or the coarse level fidelity antenna that we start with, we still can get out those high level results to see even if we're in the ballpark range of what we expected. And if not, maybe that gives a great indicator before even upping the fidelity and calculation time of other issues that may need to be mitigated or fixed. Okay? And this allows us to just get that general picture, and if we were satisfied with the results here, we can then move to up the fidelity. Once again, just like for the thermal characteristics or even the computational fluid dynamics. And in our case, we've just been using ANSYS for the other two fields, and we did the same with the antenna design. In this case, we used HFSS, and what this allowed us to do is to take our 2.2 gigahertz omnidirectional pattern and run it through some type of co-site analysis to see how the signal and energy is being interfered just by the satellite body itself. And we were able to then generate a brand new pattern that is of higher fidelity than the one that we just previously saw. In the case for us, what you're going to see is you're going to get a contour that looks much more jagged. As you see here, it's not just clearly defined. And its gain contour pattern on the ground now is a much more realistic representation of what would actually be seen. It wouldn't just be a single circle that's very neat. It would be very much dependent on certain aspects that really give us this contour on the ground in the way we see it. And because of this now, we may get more unexpected dropouts in certain areas and dips that we didn't account for with just that idealized version. That with this can help us once again paint a better picture for how to mitigate these issues and deal with any types of initially unforeseen problems that we could not detect with just using the coarse antenna. So once again, all of this though ties back to my mission. With the proper antenna design, with the proper thermal design, with the proper CFD modeling of the aircraft, the thermal characteristics, and the communications platforms, am I still able to guarantee myself a mission success, right? And this is where now you would be able to kind of go in that whole process. All of these things need to play in with each other. So as we have our X-43 hypersonic vehicle taking off, we need to have our EOIR sensors above properly transferring or going through their analysis at the same time of having all the communications layers and satellite orbits playing with one another. We need to model the entire operational environment like we see here on screen to truthfully ensure that we are able to deliver accurate results in a seamless single environment. And now you can probably picture also with what we see here that what the users would have learned using SDK with all these different portions of the aviator, EOIR communications could then be applied to other programs that also involve aircraft, thermal analyses, or even communications analyses. So we're really just showing the different facets of DME right here by showing that we're able to bring in various models that are either user-defined or user-calculated from external tools and leverage them together with what our multi-domain physics-based environment has to offer. So the biggest takeaway to remember is you need to target an ecosystem that connects the different mission, system, subsystem, and component models that link back to a multi-domain physics environment. That is the most single important thing. We can't just focus on the disparate pieces and the disparate models in each of these different portions, like in testing or training. We want it all to link back together to make sure that we're focused on the mission. And although the Digital Engineering Initiative is still fairly new, AGI has spent the last 30 years developing STK. So as we saw, STK does allow us to model different models that are open and data-driven, such as performance models of aircraft, sensor models, communication models, and various threat models, as well as integrate with various other tools. We know that there's going to be many tools where other high-level analysis is being done, such as ANSYS in our use case, or even Excel or MATLAB, that need to be brought in. So STK has the ability to really scale up and open itself up to various applications. And we do believe that because of this, STK has a large role in the DME and MBSE realms of both the aerospace and defense industry. I really appreciate everyone for attending, and now we're going to go ahead and move on to the questions portions and any next steps of the webinar. So I really appreciate everyone attending this webinar today, and I really hope you learned a lot about both digital mission engineering and how to apply this to your engineering lifecycle, even if it isn't focused around hypersonic vehicles. So if you look on the screen here, you can check out our virtual events at agi.com/events. Please reach out to Dwayne Barrett for any type of consultations with DME or any related questions. If it gets more on the technical side, you can reach out to myself at msyed@agi.com or reach out to our general support line. They are very helpful and very experienced at using SDK and really can help you implementing SDK into your organization. And to go even further, we do have some documentation that is really an expert recommendation on how to implement DME at your organization, or at least the very start. So with that, I'm going to just open it up to any questions. And I'll leave it back to you here, Dwayne, for any closing remarks. Thanks, everyone.